Hello, everyone. Thank you to the Native Plant Society for inviting me to give this talk. The title is Phenological Shifts Over 25 Years in Herbaceous Forest Plants in an Illinois Remnant. My name is David Zaya. I'm a plant ecologist at the Illinois Natural History Survey, which is part of the University of Illinois. This work is done in collaboration with Carol Augspurger, also from the University of Illinois. And my name is first on this slide because I'm giving the talk. One thing I would like to mention before I start on the presentation is, what is phenology? I'm going to use that word a lot. And what I mean is kind of life events that happen in biological systems. Often when we talk about phenology, it's repeated events, and often those events are repeated every year, so annually repeated events. And that is the case here. And in particular, we're talking about the phenology of herbaceous, non-woody species in a forest. Previous research on the phenology of herbs has found that they're flowering earlier as time has gone on. There are many long-term studies, mostly going back decades, but a few going back drawing upon observations from the 18th and 19th centuries. The famous example from North America is the study that looked at observations that Henry Thoreau made in Massachusetts in the 19th century, and then went back to the same places and looked at the same species and found that they were flowering earlier than they had previously. When people look for weather variables that predict these earlier flowering dates, they usually find that it's temperature in the preceding month, but in general they exclusively look at temperature variables. There's little knowledge of other events in a life cycle, especially vegetative events, things like when leaves first come up or fall off or finish expanding in spring. And as far as we knew going into writing our manuscript, there was no study that explicitly showed a concordance of temporal trends in phenology and weather. So if a weather variable that explains a phenological variable is shifting in the same way as that phenological variable. If there are shifts in timing of life events, it could have some important implications. First, it would be a biological validation of global climate change. If the growing season is affected in terms of length, that could have that could alter productivity of terrestrial ecosystems in important ways. It can also be important for carbon and nutrient cycling. Species interactions could be affected. There's all types of species interactions that are candidates, but the one I'm thinking of in particular is pollination. Demographic rates could be affected, which things like survival and reproduction growth rate, which then could affect population size and abundance, either positively or negatively. And there are interesting ecological and evolutionary responses to look for. Are shifting phenologies and changing climates challenging the limits of plasticity and how rapidly evolution can occur? So a formal statement of the hypothesis that we wanted to test is temporal shifts in multiple phenological events for herbs are concordant with temporal changes in weather. And I'm highlighting multiple phenological events. We're not just looking at flowering. Put another way, we wanted to know, is phenology shifting through time? And if so, is it in a manner consistent with climate change? I want to emphasize, this is, if we find evidence, it's correlative evidence. we're limited in what we can say about causation because this is an observational study. So a bit of a visual, right from the start, when we were thinking about analyzing and presenting this data, we talked about a three-legged table to support the hypothesis. First, we want to show that there's a change in phenology, like when events happen, how long these phenological events last. Then we'd have to show that the phenology is predicted by a weather variable. And finally, that weather variable is changing through time in a manner that's concordant with or consistent with the change in phenology. This study occurred at Trelease Woods, an old-growth forest northeast of Urbana that is increasingly dominated by sugar maple. There were 25 plots in which data collection occurred, each 1 meter squared in size. The plots were separated by 50-meter intervals across an area of the forest that covered 4 hectares. 43 native herbaceous species are included in this study. Data were collected on an additional 7 species, but they weren't numerous enough to analyze. The phenology of the 43 species varied greatly. This is a visual representation of their phenologies, when events occur, how long periods last, things like flowering and mature leaf period. And you can see huge differences in how much of the year they're up, what parts of the year, etc. Here's pictures of some of the species that were found at Trelease Woods and included in this study. If this was a live presentation, I'd ask you to shout out some names of these species, but since it's a recording, I'll just give you 10 seconds to look them over and come up with some guesses. Good job. Yes, that's right. Data were collected over 25 years, either weekly or every other week, except in winter when it was sometimes less frequent. And at each plot, multiple species could be present. For each species, the species identity and its phase, current phase, were recorded. What do I mean by phase? Well, the phenological events, 6 phenological events were delineated for these species. Associated with spring, we have when leaves emerge and when they're done expanding, the beginning and ending of flowering, and then associated with autumn, when senescence begins, when leaves start turning yellow and falling off, and when dormancy begins. That's when the last leaf has senesced. From these events, durations of phenophases, 4 phenophases, were determined. So that's the leaf expansion phase or period, the flowering period, senescence, and the entire growing season. There are some strengths to this study that I'd like to highlight. It's conducted in a natural setting, in an intact old-growth forest, and data are collected on the entire community, not just a handful of target species. It's quite long-term, 25 years, and the data were collected by a single observer the whole time, which has the advantage of increasing consistency. There are multiple marked plots, which has the advantage of shedding some light on spatial variation and variation within a species. And there are multiple points in phenology, not just flowering. We use temperature and precipitation as potential explanatory weather variables, not just temperature, which is what most studies do. For data analysis, we divided the species into three seasonal groups. We use seasonal groups to increase the relevance of weather variables tested as predictors. And those temperature and precipitation weather variables came from an Urbana weather station. We use linear mixed effects models for the analyses, and those models were applied to the three legs of our table. So did a phenological event, its timing change through time, through the years? What weather variables predicted that event? And did the weather variables change in a similar pattern? So, our first question, did phenology change through time? Here's a summary of the significant changes in event dates for our 6 events. Data are broken down into early and late species. I should say negative values represent advances, so things are happening earlier, and positive values represent delays, meaning things are happening later. In general, things tend to be happening earlier. The big exception is when senescence occurs for late species. So those very late summer and fall senescing species, they are beginning to senesce almost 1 month later now, on average, than at the beginning of the study. Species differed greatly in the degree or direction of change. So I'd like to highlight the emergence of late species. They weren't significantly different than 0 as a group, so there's no bar present. But when you dig into that group, you find that there's quite a bit of variability. Some species are emerging 3 days earlier per decade, things like Pilea pumila, clearweed, and other things within the same group are emerging 2 days per decade later, things like Geranium maculatum. Another thing when we look at the changes in event dates, the shifts were not consistent across phenological events. For example, when you compare when leaf expansion ends to when senescence begins, those variables are not moving or not changing to the same degree and not even changing in the same direction. Differences were evident across seasonal groups. So comparing early to late species, we can see that expansion is ending earlier for both, but that shift is greater for the late species. Whereas for beginning flowering, early species are flowering earlier, but late species are not significantly changing as a group. And the biggest differences was for when senescence begins. Early species are senescing at about the same time across the study period, whereas late species are much later. When we look at phase durations, in general, the duration of spring events is much shorter. So when leaves are expanding, that's happening much quicker. Flowering times are a bit shorter for late species, but in general, this duration is affected less. Senescence is happening much faster for those late senescing species. So fall is biologically, for these herbs, occurring over a shorter period of time. And when we look at growing season for the late species, it is much longer, over a month longer since the beginning of the study. And that's driven by earlier springs and later falls. Overall, for a given species, most events are advancing and most durations are shortening. There's a bonus data set that I didn't tell you about from the start. Carroll found the records of the former University of Illinois Natural Areas Coordinator, who recorded phenological events from 1948 to 1964 for 8 species that Carroll had data on and 6 events that matched very closely what Carroll was recording data on. And so we did a comparison to see how things from 1948 to 64 compared to those similar data from 1993 to 2017. And what you see here is a very big table, but I've highlighted the significant differences. The orange highlights show things that are happening significantly earlier, and the green highlights show things that are happening significantly later. So let's go through an example. Claytonia Virginica, the first species in this table. Emergence is happening statistically at the same time. Same thing for end of leaf expansion. Flowering is beginning statistically later, but it's ending earlier now than it was in the 50s and 60s. Beginning of senescence is occurring earlier now, and beginning of dormancy is occurring earlier now. And it's, for most species, most events are occurring earlier. The exception is Laportia canadensis, wood nettle, where the recorded events generally are happening later. So going back to our three-legged table, do we have changes in phenology? Yes, sometimes. Not all events are changing and not all of them are changing in the same way, but we definitely have some substantial changes in phenology. Then we looked at weather variables that could predict these phenological events. I won't go through the details of all the weather variables that we looked at, but I'd like to highlight that we have both temperature and precipitation variables. And also, those first 2 temperature variables listed are the most important ones. And there's the mean daily mean temperature and also cooling degree days. And cooling degree days is a measure of hotness. We found that in 12 of 13 cases, there was a weather variable predicting the phenological event. So let's look at a quick example. Beginning senescence near the bottom for early and late species. For early species, May temperature predicted senescence, and for every degree increase in May temperature, we had 1.7 days earlier senescence. For late species, September temperature predicted senescence, and for every degree increase in Celsius for September temperature, we had almost 3 days later, that's a positive value, 3 days later senescence for those late species. So regarding our second leg, is phenology predicted by a weather variable? Yes, usually that is the case. And for that third leg, we're looking for concordance between the phenology changes in phenology and changes in weather through time. And what you would look for here is red lines, the red solid lines showing a significant change in the red phenological event date, and then a black solid line showing a significant change in the weather variable that best predicts it. And in 6 of 13 cases, there was a shift in phenology, there was a shift in weather, and the two things were concordant. So in 6 of 13 cases, we've built that three-legged table. So are there changes in weather variables that are concordant? Yes, sometimes. So to summarize, we have support for the hypothesis that climate change is associated with changes in some, but not all, phenological events. The changes in phenology are not uniform. They are specific, they are event-specific or phase-specific. So it depends whether you're talking about flowering or senescing or whatever the case may be. And they're also species specific. The different species vary a lot in this respect. This is the first long-term multi-phase study of an entire herb community. So it's not just flowering and it's not just a few species, it's most of the community. We've shown that responses among species can be pretty complex. So we can't say that all species are shifting earlier or later in the same direction in the same degree. And even within a species, those shifts are not consistent. So different phenological events and phases are changing differently through time. This can have implications for species interactions, things like pollination and herbivory, but also competition amongst the plant species. There may be evolutionary responses or a lack thereof, and it's also unclear how this affects the light available for photosynthesis for these plants, especially in light of canopy closure in spring. Well, yeah, in future studies, Carol also collected data on the woody species of trellis woods, and we're currently analyzing that data now. And also, in the future, Carol wants to explicitly test how canopy tree and the light they allow to filter through is associated with herbs' phenology and when they can have light for photosynthesis. Thank you, everyone. And also thank you for people who've helped us and organizations that have provided data and funding, including the University of Illinois. And I look forward to your questions. Thank you.